For the last decade, deep learning has been built on a hidden assumption that training will always happen inside data centers with virtually infinite memory. The industry standard for optimization, stochastic gradient descent, was designed for this environment. It assumes a massive compute cluster can cache every single intermediate activation in memory. It also relies on high-precision numerical formats. SGD maps a continuous, smooth loss landscape, requiring 32-bit floating-point precision to calculate tiny gradient changes without the math breaking down. But the physical reality of edge computing, local silicon, mobile phones, and IoT devices breaks both of these assumptions. Edge hardware operates under severe thermal and memory constraints. To fit a modern parameter model onto these devices, the weights undergo aggressive sub-byte quantization, compressing standard floats down to 4-bit integers or block formats like Q40. At the same time, we expect these localized models to adapt as they process an infinite stream of real-time sensory data. When you pair standard backpropagation with continuous temporal data, you trigger backpropagation through time. BPTT must cache the sequential state of every layer at every clock cycle. On a constrained device, this triggers a catastrophic VRAM explosion. Even if you could solve the memory limit, standard gradients fail mathematically here. When forced through highly discrete, quantized bit spaces, SGD suffers from severe gradient vanishing and explosion. The math stalls out. The Welvet engine reconfigures network topology into a volumetric space. It abandons continuous space-directed acyclic graphs and the global chain rule to solve these hardware bottlenecks. To achieve continuous on-device learning, the entire concept of monolithic backward propagation has to be discarded. Traditional frameworks represent neural networks as one-dimensional, sequential lists of layers, known as a directed acyclic graph. This sequence creates a global execution lock. Intermediate layers are locked in place. They cannot update weights until the forward signal reaches the final output and unwinds the tape entirely back to the front. Meanwhile, every intermediate activation state must be held in VRAM. Welvet replaces this flat topology with the volumetric grid. Networks exist as a 3D matrix of discrete cells. Tensors route directly between distant coordinates. But standard backpropagation here fails. Distant branches idle, waiting for partial derivatives to traverse this complex spatial topology. Reorganizing the physical routing is only the first step. While the 3D grid solves structural bottlenecks, true asynchronous learning requires replacing the underlying gradient math. Backpropagation requires smooth, differentiable mathematical spaces to function. When it encounters the sharp edges of quantized data, it breaks. Welvet bypasses this requirement through its tween package, utilizing neural target propagation. Instead of a derivative, the network passes an idealized activation target backwards. Receiving this, a cell calculates the error gap between its actual and optimal output. It executes a localized heavy and weight update, completely severing the global forward-backward dependency lock. This becomes critical when we examine how Welvet handles memory. The engine enforces bit-packed persistence. There are no silent substitutions to high-precision floats during execution. The storage DType is the fixed mathematical boundary. When standard gradient descent attempts to step down into heavily rounded integer spaces, it shatters against these non-differentiable walls. The tween gap method, however, bypasses continuous derivatives. It calculates an exact differential that acts as an informed, localized bit flip mechanism. By switching to target propagation, sub-byte quantization goes from being a mathematical roadblock to a native computational environment. Base target propagation does have one inherent bottleneck. As you pass targets backwards through deep networks, the mathematical signal degrades. The architecture resolves this through topological partitioning, specifically using the split training modalities. Tween split bisects the volumetric grid into distinct, autonomous modules. Instead of waiting for an error signal from the final output head, these boundaries act as fresh injection points. They introduce local targets mid-network, short-circuiting error degradation before it cascades. To generate intermediate targets, the system uses proxy-accelerated generation. Auxiliary micronetworks are grafted onto intermediate cells, instantaneously estimating the ideal target. Efficient fast proxies operate strictly on bit-packed weights, stripping out heavy matrix multiplication to make target generation latency-free on consumer hardware. This structural design peaks with the asynchronous execution mode, tween split head proxy async. By assigning these proxy estimators to discrete hardware threads, the primary volumetric grid continues processing live user inference completely uninterrupted. The network trains itself in the background. Deploying proxy-grafted split topologies successfully decouples the forward inference loop from the learning phase, achieving zero-latency edge adaptation. To verify this architecture, Welvet engineers conducted an assessment of over 500,000 matches, comparing 28 target propagation modes against standard SGD across 34 specific data types. This chart visualizes the Lucy score, a composite metric of throughput, availability, and accuracy. Across all matched cells, non-SGD modes achieved higher raw accuracy than SGD in 98% of configurations, with tween split and its proxy variants dominating the win counts. The Lucy score is paramount for edge computing. It heavily penalizes training modalities that block live inference duties to perform their weight updates. The tween split variants dominate this specific metric because their asynchronous nature keeps the infer and train duty cycle high, maintaining near-perfect availability. This table highlights performance on quantized data types, including 4-bit float, 2-bit integer, ternary, and binary. In these conditions, non-SGD training architectures hold an 81% Lucy score win rate and a 100% accuracy win rate over standard gradient methods. Standard backpropagation and mesh BP remain mathematically optimal strictly for offline, high-precision float32 pre-training on unconstrained hardware. For continuous deployment on the edge, the data points to a definitive apex configuration: mesh, tween, split, sparse. Every word in that execution mode serves a structural purpose. Mesh provides the three-dimensional routing. Tween provides the local target propagation. Split establishes the autonomous computing zones. And the final component, sparse, applies statistical epsilon thresholds to the updates. Only the most active or misaligned spatial nodes receive parameter adjustments, strictly guarding the limited power budget of the edge device. By abandoning the legacy chain rule in favor of proxy-accelerated target propagation, AI architects can bypass the massive memory bottlenecks of backpropagation, running continuous learning cycles directly on edge silicon.